Welcome to Data Structures. If you're watching this, you're probably somebody enrolled at the actual physical class at Berkeley, CS61B, but if you're just some random person from the internet, you're welcome too. All the material will be here available on the web for you to learn. Everything's free, so hop in. So what is this class? Well, this is a second semester class, as most of you at Berkeley know, and it is, to me, one of the most important classes. I'm a little biased because this is my baby and the class I've spent the most time developing and thinking about, but this is the class where you go from being a basic programmer, knowing how to kind of build stuff, and really working your way towards independence. It's kind of like boot camp. This is the class where when you leave it, I want you to be able to walk into, say, Google or Airbnb, do an internship, blow people's minds, do well. This is the class where when you're done, I want you to think, okay, there's some thing I want to achieve. Maybe I want to learn to build an Android app to, I don't know, connect children in countries so they can compare Pokemon or whatever it may be that you want to build. This is the class where I want you to get the independence and the skills necessary to go out there and do anything else that you want to do. The great unlocking of all things out there. Okay? So how are we going to do that? What is the framework of this going to be? Well, this class is fundamentally about efficiency, okay? And it'll connect us to this notion of independence, as we'll see in a moment. So first, the first way in which we might consider efficiency is in our programs themselves. How long does it take the computer to run the program? How much memory does the program use? And to understand that, we're going to study a certain set of algorithms that are really good ways of solving certain problems, and data structures, ways of keeping our information organized so it could be rapidly retrieved and modified and so forth. So that'll be an important goal. But arguably more important is learning to be yourself a more efficient programmer, to spend less time to build the same complexity of program. And so to do that, we're going to, along the way, we're going to learn to design, build, test, and debug large programs, so over 1,000 lines or so. And what that's going to do is give you an opportunity to approach a specific problem and really beat your head against the wall a little and think about all the different trade-offs that might go into how you might design a program. So in previous classes, you've probably mostly been given a set of functions you fill in. That will not be the case for much of this class. Along the way, we will also learn to use a set of programming tools. We're going to use a bunch of real-world tools, principally Git, IntelliJ, and JUnit, and we're going to learn Java as we go. Now, Java is not the goal of the class, or this is not a Java programming class. We just needed a language which is popular and is used for large-scale programs, and it is both of those things. But it could have been other languages. And we're not really going to focus on Java so much, though we'll have to at the beginning just to get up to speed. So this class assumes you already have a fairly solid programming foundation, that you know what object-oriented programming is, and you've done, say, class definition, that you know recursion, that you've dealt with lists and trees, and we're going to build from there. So why is it that if we're going to try and learn to be independent programmers, why specifically are we focusing on data structures and algorithms? Why isn't this, say, an Android app development class or a robotics class? Well, for me, data structures and algorithms are a particularly interesting and very general class of problems that have all kinds of neat stuff to them. So one of them, of course, is that our daily life is only possible because of really advanced algorithms and data structures. So of course, if we open up, let's see, I'll do another Google tab here. We know autocomplete, and we know that it seems to work well, but it happens so seamlessly we don't even think about it. So we might do something like, how does autocomplete work? Okay, hey. And you'll notice that as I'm typing, like, what are snails good for, or whatever. What are snails even trying to do? That is a good question. Let's see. What are they trying to do? Well, you can read later. I bet there's some good stuff in there. Anyway, we can see that as we're typing, that the Google search box here, it responds instantly. Like, how is auto, yeah, or whatever it may be, just happens instantly. As soon as I press a button, boom. And that is enabled only because they're using the right data structures and algorithms. And in fact, at the very tail end of this course, we'll talk about the specific data structures used to support this. Another big thing is that algorithms and data structures are really driving what's changing in our lives right now. So here is a Google self-driving car prototype. So Google, Uber, other companies are really pushing hard on, and Tesla, of course, are really pushing hard on building cars that drive themselves. And that's going to have just insane implications. Like millions of jobs in the United States are going to disappear in the near term. Something like 1 million or so people a year are killed in car accidents around the world. And so we're going to see just tremendous upheaval as these become state of the art. And it's the algorithms and the data structures used to store all the information that as this car is learning that allow this to come to happen, to be able to make these big changes in our lives. Another, of course, is, well, data structures, it turns out, having a good handle on them is perhaps the most important thing for being a good programmer. So the creator of Linux, Linus Torvalds, says, the difference between a bad programmer and a good one is whether the programmer considers code or data structures more important. Bad programmers worry about the code. You know, what does it look like? What kind of, you know, do you use tabs or spaces or something like that? Good programmers worry about data structures and their relationships. And you'll see this when we get to project 2. If you make the right choices about the data structures you need to implement this database system, then you'll have a much easier time. But if you make bad calls about the class hierarchy or about how you're storing information, your life will be much more difficult. And we'll see that again in great detail in a few weeks. Another reason that this is a fun topic is just for intellectual stimulation. So there's a lot of neat little math problems. I don't know if you ever tried to draw this house. So the goal is put down your pencil in a corner and then try and draw the house without picking up your pencil. So maybe I go there, 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 there. Uh-oh, I missed a line. I mean, you couldn't tell because you couldn't see me drawing, but try it out. So it turns out it is possible to draw this house without picking up your pencil. However, it is not possible to cross these 7 bridges in this town without having to basically hop. You can't do the equivalent of drawing the house over here. And so there it turns out that you might ask yourself, why is that? Just from a mathematical perspective, I'm just curious. Why can you draw this house? Why can you not draw this? Is there some simple rule? It turns out there is, and we'll talk a little bit about graph theory later in this class. And so if that's an aspect of computer science you find interesting, that is theory, this is a class you'll get a little taste of theory as well. Another big reason we're curious about algorithms and data structures is that if we can develop so it's important in the modern scientific world to be able to program. It's important to be able to know what algorithms are out there, what appropriate data structures you need to write simulations, because that's the direction science has gone. And so one interesting example here on the left, this is a video of starlings flying around. They're a type of bird. And this is a simulation on the right showing that we're able to recapitulate the essential behavior of this flock. And so you can do fun things where you start sending, say there's a hawk, chasing them around. Here, I guess you can't quite see the hawk, but because of the fact that we write a simple model that's able to demonstrate the same behavior, it implies that we know something important, potentially, about how these birds are behaving. And this is also used in other areas, like in, say, protein folding, in galaxy formation, all across the board. Simulation is a really important tool. And not just in terms of understanding and proving to yourself that you know how the universe works, but you can imagine also maybe this algorithm the bird is using could actually be useful for some real-world application. Say, I don't know, swarming flying drones or something. Another nice thing about algorithms and data structures is that with really good knowledge of them, even if you're, say, in for this only for the aesthetics, only for art, there's some neat things you can do. So here's some realistic fluid simulations using some clever fluid dynamics algorithms. So that's plenty of this is all simulation. So you can build lots of those stuff. Another particularly beautiful thing, before I get there, so for my students at Berkeley, I just want to throw out there that if you like watching fluids flow, like those simulations, nature's best fluid flow show, the ocean, you may not realize that living in the Bay Area that waves get really, really big. So on January 21st, there will be some 35-foot waves. So maybe go to the beach and check those out. But back to computer science. Another rather beautiful thing here is the, of course, recently, Go playing computers have done well. So AlphaGo beat the world's best players. Totally swept the entire tournament and even beat the world's reigning champion. And I really like this quote from the reigning Go champion, that after humanity has spent thousands of years improving tactics, computers have told us that humans are completely wrong. That is, we cannot compete. So what's interesting about the way that this Go computer played is it played unlike a human. It did weird stuff, and it still managed to win. And so the reigning Go champion said, I would go as far as to say not a single human has touched the edge of the truth of Go. So leave it to a Go player to say something really poignant and beautiful, poetry, just from your profession. Good job. Now, not everybody's impressed. There was a guy in the internet comments section who said, the rules of Go are quite simple, and the resources that you have out there for learning it are gigantic, and no one was surprised except for poorly educated losers. So I don't know. Internet comment sections, they disagree, but I still think it's beautiful, even if this guy doesn't. And lastly, another big reason that we might study algorithms and data structures is, well, it sure seems like a popular thing for people my age to be doing. So at Berkeley, most of the students here, we're largely 18 to 21, not everybody. And it seems like everybody else, people look like us, we're all doing this thing. It must be important. This year, the 61B total enrollment for data structures is going to be, we're estimating just shy of 2,000 students. We currently have 1,350 enrolled. I anticipate we'll have 1,250 at week 4. So this is the entire history of 61B's enrollment. And you can see here, this is the dot-com boom and then the crash that followed. Now, even the dot-com boom, which was a big deal at the time, we're completely annihilating the enrollments of that time period. And in fact, if we think of the post-boom period, the number of students currently enrolled this semester, spring 2017, is 1,250, which is the equivalent of everybody in the years 2004 through 2007 combined. So that's pretty amazing. So there's something in the water. You guys are going nuts for computer science and data structures in particular. So hey, social proof. So that's a story. That's why I like algorithms and data structures. And I think this class, I hope you'll find, is just a really good introduction to being independent, being able to build all of those beautiful things, from self-driving cars up to Go playing robots. There's plenty more you'll need to learn, especially if you're doing AI. You'll have to learn lots and lots about state-of-the-art algorithms for those specific areas later. But this here is the foundation of independence. I would ask you who you were, but you're watching a video. So you can maybe talk to the screen to yourself and explain who you are and pretend that I'm listening. I'll pretend like I'm listening. Okay, good. Good to meet you. Sorry I couldn't actually meet you. It'd be super cool. I would really like to be able to divide my consciousness into, like, I don't know, thousands or hundreds of thousands of copies and talk to everybody. Sadly, can't do it. So a little bit about us. So this semester, the Spring 17 staff, if you are an enrolled student, there's me. I'm Josh Hugg, by the way. I'm a teaching professor here at Berkeley. I have an office in the building. You can email me. This is my 4th time teaching this class, 2nd time doing this version of the class. And here are all of the teaching assistants. And in addition to all these teaching assistants, so I won't even name because there's so many, we also have a bunch of tutors who will be there to help people out who need a little extra help. We'll talk more about that later in the semester. And then we have a bunch of lab assistants, aka academic interns, which number around 140, who are our volunteers, so thank you. None of them are here, so can't meet them because I'm just at my house, but that's that. Now I mentioned, by the way, in case you're curious, you can look at, I did, since there are so many of them, I was curious, what is the letter distribution of the names here versus English? I won't talk about it here in this video, but hey, kind of fun. All right, for me it was. So that said, we're going to talk soon about the way that you learn and what in the course you can use to gain additional knowledge. And I like this little example because I, as somebody who grew up, when I was a kid, I had adults always telling me, like, you're super good at math, like, or whatever. And I didn't really understand that practice makes you get good at things. And in fact, the thing that taught me that, this is embarrassing to admit, is Dance Dance Revolution. Okay? So those of you who are not familiar, Dance Dance Revolution is a game that musically plays and stuff like the sparrows. And these are some beginning players. And you can see, this is where we all start out with playing. On the right here, somebody has a so long ago, I had a job where I had nothing to do, and I was just putting on I didn't quite get to this level of good, but I got pretty close. And that was actually a really important moment for me because I realized, you know what? That's actually how people get good at things. And so right now, you may be here, but ultimately I want to get you here. And I think that after you finish a whole computer science program, even if you're somebody who to this point has thought, am I really good at that? Because it could be really intimidating to be in a room full of people who have been programming, for a decade. You're 18 and they've been doing it since they were 8, to feel like, could I ever possibly compete? but really you can. Now, it is of course true that people with more background and people who have learned to think in a certain way, they're going to learn more quickly than you. So, but the important point here is that I really think that the ceiling, that if you had, a year to really spend on this class, and especially if you're somebody out there on the internet, if you're in the middle of nowhere, I mean, great, glad you're here. I think you can really get super good at this. Even if you feel like you're somebody who hasn't been a natural at this, right? Being a natural, whatever that may mean, sure, it helps you learn faster, but the point is that with practice, I'm pretty sure almost anybody can get up to about this level. So how do you learn? Well, you'll learn a little bit watching these videos. Now, especially if you're somebody who's just watching the videos online, watching me talk is maybe vaguely entertaining, and you'll get an introduction to the new material. But this is only a small minority of the manner in which learning occurs. Same deal with reading. Like just sitting there and reading the online text, you'll get stuff out of it. But really where stuff happens is when you yourself are actually programming. Learning is seeing a problem, figuring out a way to approach it, hitting a brick wall often, and then finding a way over that brick wall. So in this class, doing the labs, the homeworks, and experimenting on your own will give you a chance to learn all the basics, say Java syntax, learn a little bit about algorithms and data structures, and get a chance to learn the tools for this class. If you're a Berkeley student, you will also have discussion section, where you'll get a chance to practice with the concepts and argue about approaches to problems. And then we'll have these big projects, which are going to be similar to the labs and homeworks. They're going to be programming oriented, but we're going to have a design component. And we're typically going to have these big systems building challenges. These will also involve writing of tests, whereas for labs and homeworks, we'll typically give you all of those. This is where you're going to learn lots of stuff. So we'll talk about course logistics in this next little segment, but I just want to say, this class, it is really, truly about making you into hopefully a great programmer. And that I believe that even if you're somebody who is maybe, say, I don't know, even a C student in your previous programming course, if you, maybe not this semester, maybe you don't have enough time to catch up, but really, if you are sentient and you enjoy this and you are even able to get if you were even able to digest the basics of programming, you can actually get really good at this, but it may take you a lot of practice, okay? So that said, we'll move on to course logistics next, and see you in that video.